how do we convert this to this? If you're a bit confused at what you're looking at, don't worry, I was too. But we're going to be breaking down this DBC format that is easy for you to understand and help you along your decoding journey. The best way I can describe this process is like one of those scenes in a movie. A character is trying to hide or encrypt some information from prying eyes and uses a book as a key to decode the message. This is pretty much what a can frame is. An encrypted message we as humans can't read, but when we decode it into a DBC format, it is easier for us to read and understand who, what, and how something is happening. So we have our encrypted message, aka the can frame. Now we need to find our book. This would be our DBC file. But where to look inside this book, you might ask? Well, for this can frame, we would use the 52A. Think of it like a page number. Once we have found our hypothetical page, we are given the information we need to begin writing our DBC formula. DBC formulas are broken out into two different sections. The first one is going to be the message syntax, and the second is going to be the signal syntax. The top is the message syntax, starting with BO underscore. And then you have the can ID. You get the can ID by converting the hexadecimal name to decimal. For our example, the name is 52A, which when converted comes out to be 1322. After that, you're going to give the original name, which is 52A. Then next is going to be the data length, which is going to be 8 bits. And that's all you need to do for the message syntax part of it. Now moving on to our signal syntax, which is always going to start off with SG underscore. The next is going to be the name of the signal. For our example, it's going to be left front tire pressure. The next number is our start bit of 16, marking the start of the signal payload. After that, we have our bit length, which is going to be 8. The @1 indicates that this signal is an intel, with the plus indicating that the signal is an unassigned value. Now there can be differences. You could actually have an @0, which would be a Motorola, and instead of a positive, you could actually have a negative, which means that the signal would be a signed value signal. If you're a little bit confused about the Intel on Motorola, basically it's going to be least significant bit, or LSB, and then if it's a Motorola, it's going to be the most significant bit. Positive means it has to be a non-negative number, and negatives can be either positive or negative. Those are the most common ones you're going to see, but there are also M and MOs, which are multiplexer signals like TDMAs, but they aren't super common, so you don't have to worry about those too much. If this all seems a little bit overwhelming, don't worry. I have a tool at the end of the video to basically show you how to plug and play in order to get these DBC formulas. After this, we have our scale and offset, basically our math formula to get the answer we need. The last is going to be our mid-max ranges and the unit of measurement. If you want to know how this all comes together, well, using our example, 16 is telling us to take the third byte. In this case, it's going to be 3F. @1 plus lets us know that it's going to be a least significant bit that is unassigned. We then times our decimal form of 3F, which is 63, by 4, giving us 252, which is inside of our range, with our unit of measurement being kPa. The tool I suggested to use when setting up a DBC formula is going to be on the CSS Electronics website. Here you can just plug and play all your data points and it'll give you a complete DBC formula. Well, I hope this video helped you DIMO decoders, and I'll see you in the next one.